Welcome back. Now it's time to move to lecture 30, and we are going to talk about quantum gases and condensates. It's really a lecture that goes hand in hand with lecture 29 when we started to look at the Fermi-Dirac distribution and Bose-Einstein distribution. And in fact, I'm just going to remind you of the summary of the previous lecture in the next slide. But in a nutshell, what we are going to do today is to look at the cases of fairly high density systems. And as we discussed at the end of last lecture, the low density approximation, which is usually correspond to a low chemical potential, can be often described quasi-classically using the Boltzmann distribution. But at high density or high chemical potential, and of course it's always relative to another energy reference, the quantum mechanical effects start to show more significantly. And we discussed two types of particles last week. Last time we discussed the fermions, those particles that have an anti-symmetric wave function and obey the Fermi-Dirac distribution. And we discussed also the boson, which has a symmetric wave function and therefore are described by the Bose-Einstein statistics. When I say symmetric here or anti-symmetric, I mean symmetric, anti-symmetric with respect to the exchange of particles. So what we did last time is to discuss the specific distribution that we have for those two types of particles. And we discussed the Bose-Einstein statistics and the Fermi-Dirac statistics, and we were able to find the distribution, so the amount of particles that are at a given energy E. And we did that using the Grant partition function. So the Grant means that we allowed the number of particles to change. And this is usually reflected in these equations by the presence of the chemical potential mu here. The fact that we are using a different, that we allow the number of particles to change. As always, beta here is 1 over kBt, so we see that these functions depend on temperature, chemical potential, and the energies, the parameters that we are looking at in terms of distributions. We saw that the distribution change a lot when we have a very small, a very large chemical potential. We have a large change, and today we are going to in fact explore this area here. We're going to explore the area where the Bose-Einstein distributions start to basically diverge close to zero, and we're also going to look at this area for the fermions where the distribution takes a large dip from about 1 to 0. So we are going to look at what's happening right here. So we are going to do the two things for bosons and fermions. What's interesting is, of course, because the two mathematical forms are similar, there is a lot of math that can be carried over between the two different statistics, even though, as we know, they are very different. And that's what we're going to do at the beginning of the screencast. And on the second part of the screencast, we will look more carefully into the specific case of fermions and then bosons. So let's try to consider now that we have a fluid, or like it's discussed like a gas, and then we are going to consider that do not interact. The particles do not interact. In fact, the entire screencast will be done under that assumption that we have non-interacting particles. But what we are interested in is to understand the statistics of the distribution of those particles in the gas. And of course, we expect that there will be some profound differences between bosons and fermions since they obey different distributions individually. So let's go for it. We are going to suppose that we have particle of spin s. That's going to allow us to have a little bit of an additional degree of freedom. And as we know, if quantum mechanically, if a particle has a spin s, the number of projections of that spin on a given axis will be 2s plus 1. So we have really a degeneracy of 2s plus 1. So if it's fairly new to you, just think about the spin 1/2, like the electron. You know that a spin can be up and down. So when we say that it's up and down, we really mean that the projection of the spin 1/2 on the z-axis is either up or down. So we have two possibilities, 2s plus 1. S being 1/2 is of course 2. So we have two spin states. So this is the simple case, but of course we have other cases. When the spin is a half integer, we have fermions, and when it is an integer, we have bosons, as we already discussed. We of course consider the grand partition function, and just like we've done before when we discussed about the partition function, it's easy to show that the grand partition function of the collection of non-interacting particles is just the product of the grand partition function of each individual particle. So this is what this equation here in the orange box mean. So what we see is that the grand partition function of the entire collection of particles is just going to be a product of all the possible states that we have times the grand partition function of the individual particles, and we have an additional power here, 2s plus 1. And this power comes from the fact that we already multiplied those partition function the number of times that we have degeneracy. So this is nothing new. We've used this before. Now what we can do is to, of course, use the grand partition function of the individual particles, and the plus and minus correspond to fermions and bosons, as we've discussed at length in the previous lecture. We are going to use these results throughout this screencast. So just to remind you, even though I already said this, it's a non-interacting case, and the number of particles can change. This is why we use the grand partition function, and the temperature is a parameter, as is the chemical potential. We are going to discuss this, of course, in details. One thing that comes very handy is, of course, the logarithm of z, and the logarithm of z can be calculated straightforwardly. Since we have the logarithm of a product, we end up with the exponent in front, and then the logarithm of the product becomes a sum of the logarithm. Nothing really new, other than the fact that this equation is going to be used quite a bit in the next few slides. Let's first look at the grand potential. The grand potential is defined as minus kBT ln of the grand partition function. Well, we just calculated this for the fluid of non-interacting particles, quantum particles, so we can just substitute here. Now, don't be scared by the math. You will see that this screencast has a lot of math, and it's very easy to be lost in the math and then lose the focus, which is really the conceptual approach that we want to do to understand thermodynamics. So, of course, it's important to understand the math and being able to do it, but it's the goal is really to understand the concept. You have to look at the math as a tool towards understanding the concept and not as an impediment to understanding the concept. So I'm going to try to provide as many details as possible for you to be able to follow along the math. Of course, this is not a substitute for you to spend time to do them, of course. So in any case, this is what we get here for the grand potential. And very often, and we've done that so many times in this discourse, is the fact that we have a sum over many states. We usually replace this sum by an integral. And the reason why we do this is because we have so many possible states that it turns out that a continuum limit, it works pretty well. And we do that by introducing the density of states. So instead of summing over all the states, we basically bunch together the states that have the same k and then integrate over them. And the way we bunch them together, of course, is using the density of state, gk. And gk dk is the total number of states that have a momentum between k and k plus dk. One more time, I just repeat the equation here. Nothing that we have not done before, but you recognize, of course, the surface area of a sphere in k space, and here 4 pi k square, and dk is the width of the shell around k, so a shell of width dk. 2 pi over L cube is the volume of a single state quantum mechanically. That's what is imposed quantum mechanically. Again, we've done this in the previous lecture. And the density of state, of course, has a factor because we have each of these states is degenerate. So each of these states have actually two s plus 1 possibilities, which are the projections the projection of the spin, as we discussed a moment ago. So this is the equation we get for GK, and this is always true in this particular system. So that allows me, instead of the sum, now we can integrate over K, but with the right weighting factor, which is density of states. So I end up with this equation here. Of course, I can substitute, and I can substitute also because here we have an integral over the energy. So we need to know the dispersion relation, which, as a reminder, dispersion relation is the relationship between the energy of a state and its wave vector. So I have to tell you that this here is usually the free particle. So it's just the kinetic energy, as you can tell. This is not the only dispersion relation that we can use. In fact, I'll show you another example later in this lecture. But imagine that we have this. We can calculate, of course, dk and substitute k squared just by a simple inversion. So we get the density of state, not with respect to k, but with respect to energy. Of course, we can do that since we have a one-to-one correspondence between k and E through the dispersion relation. So I can do that, and I can substitute, and I end up with this equation, which again has a lot of constant. But the important thing is that we do have to integrate over all the energies, and of course the energies are positive, so that's the reason why we start at 0. And the term that matters is e to the power 1/2. And again, I'd like to remind you that this e to the power 1/2 comes from the fact that we use this particular dispersion relation. So we end up with this equation. So this equation is exactly the same as the previous one, but we cleaned it up a little bit. Well, we cleaned it up a little bit. There is actually an integral in part by part to go from this equation to this equation. So it's not just a cleaning up. There is an integral by part. But the point remains is that we have an analytical formula here for the grand potential that applies to both fermions with the positive sign or bosons for the negative sign. So that's nice. We have this equation. We can also do other functions, like, for example, the mean occupation of a state. And we can calculate this using the usual formula that we have established before. Of course, we end up with the same equation that we've seen before for the Fermi-Dirac and Bose-Einstein equation. So this is the occupation of a specific state with a wave vector k. Just like to remember here to point out that k is actually a vector in 3 dimensions in k space, so it's really one single state here. We don't have an integral over the sphere as I did before. We can calculate the total number of particles again by summing all those states, or summing all the particles that are in given k state. So long as I include all the states, I'm good. And I do that again by substituting the sum over k by the integral over the density of state. So this is fairly typical. We've done this so many times. If you do not feel comfortable with this by this point, maybe it's a good moment to pause the screencast and to try to remind yourself, because we've seen it many times, and by now you should probably be able to master this well. You can do the same thing for internal energy. Of course, the internal energy is the total energy, which is basically the sum of all the energies that are occupied and weighted by the occupation number. And so we can obtain this pretty straightforwardly from this one. And I'll remind you, so it's coming from the previous slide, that the density of state is obtained as a function of energy. So here I did not substitute yet, but the density of state, this is what I got from the previous slide. I just copied. And that allows me, using that density of state, to write the number of particles and the internal energy as these functions. We have these terms in front, which are mostly constant, right, with the volume, the spin, the mass, and the reduced pi and the reduced Planck constant. So this is really just numbers here. And then we have those integral. So these integral are actually fairly difficult to calculate. This is not something that's easy to calculate at all, but we are going to spend a little bit of time showing you how to do that. One thing that's important that I did not say yet, and of course it's crucial, is that to go from these equation to this equation, these equations, I introduce z. Okay, z is actually called the fugacity. It's a e to the power beta mu. So it's basically a coefficient that's going to be extremely important to be able to understand what's happening later on. So we are going to spend a lot of time using this term. It's essentially a notation to make things a little bit simpler in terms of notation, but it's a term that depends only on temperature and chemical potential. So basically, it's a term that allows us. It's a dimensionless term that will allow us to analyze the different regimes that we can get. So the fugacity z equal e to the power beta mu. This is a very important definition. I will come up at least 2 more times in this screencast. I will show you again this. I know that sometimes it's hard to remember everything as you listen to this. Okay, so here is already a reminder of the definition of the fugacity that only depends on temperature and chemical potential. So if you go back to the previous slide, you will see that the two integrals that I have to calculate, to evaluate, are of that form with a different value of n. And people have spent time, mathematicians have spent time trying to solve this. And you can actually solve it exactly, but by introducing new mathematical functions. So for those who like mathematical physics and like to explore mathematical functions, this is a delight, of course, because we have 2 of them here. In fact, there is even a third one. So I'm not going to spend time on this more than saying it. It's just basically an equation that you can find in tables, but let's try to understand a little bit what we have here. First of all, we have the so-called polylogarithm function, which is Li with an index n. And it's a very important function that we are going to use a lot in this screencast. It's a function here that I just represent from 0 to 1, but it doesn't have to be between 0 to 1. But at 1, it takes actually those zeta function that we see quite often in thermodynamics. It's called the Riemann zeta function, which of course, this is the polylogarithm function with z equal to 1. I mean, you can see fairly quickly the relationship. And then, so this is at z equal to 1. And then, of course, we use the gamma functions, which is obtained by this integral. And the gamma function is actually a function that works for any n. But when n is an integer, the gamma function actually reduces to the factorial function like this. So you can see, for example, at n equal 1, this is the factorial of 0, which is 1, and you can see that it's exactly where you were here. Okay. At 2, it's also factorial of 1, which is 1. It's the same value of 1. At 3, factorial of 2, which is 2, and it's exactly where we are right here. Okay, you get the idea. The point is, we now have a way to integrate this particular integral. It's an integral that we see quite a bit in this. We're going to see quite a bit in this screencast. So nice. Remember, now we can actually remember that we had the number of particles as a function of that integral. Now we can substitute and use substitute by the result from the previous slide and obtain this more compact version of the number of particles. I'd like to also tell you that we reintroduce here the thermal wavelengths that we have encountered quite a few times in this lecture, in this course, and it's going to come in handy again. I remind you a little bit what it is later. We can also calculate the internal energy using, again, the equation that we had 2 slides ago, but now using the formula that we have seen for the integral that we had. And then we can calculate the grand potential as well. One more time by substituting the integral that we had, and then the definition we had from the polylogarithm function. And one thing that is good to remember is that the grand potential is just minus 2/3 of u. This is a result that we had seen before in this course. One thing that you have to, maybe it's a good idea to remember, is that I have a good idea of what's happening with the Poisson logarithm function. These are the behavior of 5/2 and 3/2. These are the functions that are pretty well behaved, actually, in this area 0 to 1. And of course, the z, that's another a good thing that for me to remind you, the z component here is the fugacity. So why does the number of particles, the internal energy, and the grand potential depends on z? Well, because z is essentially parameters of the problem. B is 1/kBt, mu is a chemical potential. So we know that all those properties will depend on temperature and the chemical potential, which makes sense in this framework of the grand partition function that we have decided to adopt for all the descriptions that we of the quantum gas. We can apply the three equations that we have just described in the previous slides. You can use them for a particular case when we can make uh, a further approximation for those Poisson logarithm function. And we are going to apply this to ideal gas. So the ideal gas we know uh, correspond to a very low density, right? The density is low, therefore there is no interaction between the particles. The particles do not get a chance to interact. Therefore, the ideal gas description is very accurate. So if we have a very low density, as we already remind you last screencast, that means that we have a very low chemical potential, right? Therefore, if we have a very low chemical potential, the fugacity is going to be very small. Now, if you look at the graph of the Poisson logarithm function, you see that if z is very small, we have an almost linear uh, relationship. In fact, you could do a Taylor series and see that we have very good description of those Poisson logarithm function as a linear term. So that means that the Poisson logarithm function is pretty much like equal to z. That's nice because I can simplify, of course, all those equations and then end up with just n depending directly on z. Can have the internal energy and these two terms actually simplify, and the same for the grand potential. Now let's try to go back here and understanding a little bit what this means in the interpretation of this. We have the volume here, and in fact, we also have a volume. If we look at here with lambda cube, the thermal wavelength cube. So this means that each particle, when you look at this, the total volume that's available to them is V, right? This is the volume of the system. Lambda cube over z being dimensionless, lambda cube over z is essentially the volume that's occupied on average by each particle. I mean, you can also have 2s plus 1, the degeneracy, of course, 2s plus 1, by 2s plus 1 particles. It's more accurate like this. So just to repeat. So lambda cube divided by z, essentially the volume occupied on average by 2s plus 1 particles. So you can look at that it corresponds to a case where we have indeed a low density, and therefore there is no overlap between those volumes, which justifies why we are in this low density limit. Now for the internal energy, we find 3/2 NKBT. Again, this was the result for the equipartition result, which is not surprising since we know that we decided that the energy was a quadratic term, right? It's h bar square over 2m. And again, we found also the grand potential equal to minus nkBt, which is actually minus PV. And we've seen this before. If you remember, we've seen that the grand potential for the DL gas was minus PV. So everything seems to work well. But this is a very specific case where z is pretty much equal to 0. So this is a limiting case right here. Let's try to see this at now t equals 0. So at t equals 0, the fugacity now is no longer equal to 0, of course. So we are going to see what's happening in that case. So at the Fermi, we are going to in this particular slide we are going to introduce a couple of definitions. The first one is the Fermi energy, and I'm going to try to spend a bit of time explaining you what it means here. So the Fermi energy is the highest occupied state at t equals 0. So think a little bit about this. You have a Fermi-Dirac gas, and you can't put more than one particle in a given state. So the maximum number of particles you can put in a state is 2s plus 1, right? Because they are degenerate. In a particular energy state is 2s plus 1. So if you have a certain number of particles to put in your bookshelf, I mean, think about this as a bookshelf where you can put only a limited number of books on each shelf. There will be a point where we are going to have to stack higher and higher. Well, the place where you have to stop stacking the electrons or the particles, the fermions, electron being a good example, the place where you have to stop is called the Fermi energy. And it is defined as that highest occupied state at t equals 0. So this is a definition. Now, we also remember that the number of the occupation number for a given state is given by the Fermi-Dirac distribution. And it's a good idea to play a little bit with plotting this particular function. And in fact, if you plot it, you can see, depending on the temperature, so the higher temperature, so we go from black, which is 0, blue, which is cold, green, medium temperature, and red, hot temperature, right? But you can convince yourself pretty easily that at t equals 0, so beta equal to infinity, basically, you have a Heaviside function. Well, it's easy to see, right? Because if this number ek minus mu is negative, then E minus infinity is going to be 0, so you have 1. So if the energy are lower than mu, so Ek minus mu is negative, we have 1. But if Ek is larger than mu, this is going to be a positive number, so we have an infinity here. 1 over infinity is 0. So we understand the Heaviside this evolution of this at t equals 0. So that means that it's a Heaviside function at t equals 0. Actually, the Heaviside function, for those who are more interested in those special functions, actually the step function or Heaviside function is actually started 0 and then 1. So that's the reason why we here for the Heaviside function, the function is minus the argument. Do not worry about this too much, but for those who are used to the Heaviside function being 0 to 1, this is why we have a minus of the argument here. Let's keep moving. So mu, we see that all the states are going to be occupied until mu. But we just defined that energy where the states, at which point the states stop being occupied, is EF. So that means that mu is equal to EF at temperature equals 0. So the chemical potential, so that comes here into the Fermi-Dirac distribution, is equal to the Fermi energy as defined in this green box. This is true at t equals 0. There's one thing I like to attract your attention to. If you look at the Fermi-Dirac distribution here, it always goes through 1/2 at the value of mu. That's just a particularity of the function. So this is a good thing to remember. Now we are going to introduce another definition, which is called the wave vector. Well, the wave vector is basically is essentially the same role as the Fermi energy, but we are changing the units. Indeed, we know how to connect the energy with the wave vector using a dispersion relation. And in this screencast, we are spending most of the time with this particular dispersion, right? The free particle dispersion equation. So basically, we can introduce the Fermi wave vector as the vector at which we attain EF. Okay, it's pretty straightforward. Now we are ready to go. So the fermions are going to occupy the lowest energy state, one fermion per state, so 2s plus 1 in each energy level. Let's think about the bookshelf if you can't picture this. So we are going to fill them until EF by definition of EF. So we can now calculate the number of fermions. Of course, we can calculate that by simply doing an integral over the entire density of state. And that should give me the right answer. That should give me, we are basically calculating the integral under this curve. Very good. So we do this integral here. And we can then use the density of state that we have used before, which is actually in this particular case, because we are working at t equals 0, we just go from 0 to kf by definition, because kf is the highest occupied state at t equals 0. So we integrate from 0 to kf, but this particular density of state is of course provided is provided by the Heaviside function. One thing I like to tell you is that this integral here is over k. This Heaviside function here with 1 is over the energy. So you can do just the substitution from the integral that we've calculated so many times, and you find that the number of fermions is going to be related to the cube of the Fermi, the wave vector, the Fermi wave vector. That allows me, of course, to calculate the Fermi wave vector backward. If I define capital N divided by V as a density N, I can just rearrange this and get what is my Fermi wave vector given a certain particle density of particles. And obviously, as you can imagine, if I know kf, I can calculate ef, and of course ef is going to be also related to the density of particles here. The larger the density, so the larger the number of particles to put in the bookshelf, the larger EF. So the larger the energy, the higher the bookshelf you have to consider, the shelf in the bookshelf that you have to consider. If you can put a lot of those particles in the degenerate state, of course, EF goes down. This all makes a lot of sense. Now, if we look at T larger than 0 behavior, and here I'm sorry I didn't put the legends, but I think it's pretty clear that the higher temperatures are in red and the lower temperature are in blue. We can see that the occupation number, so the probability of a system to be of a particular state to be occupied, is given by the Fermi-Dirac. But we also know that the density of energy go as a square root of the energy. This is something I introduced early on in this screencast, and of course, what matters is the product of the two. And so we see something that goes like this. One thing that's interesting is that even when we have fairly high temperature, because the red curve is actually fairly high temperature, we still have a fairly sharp transition between the occupied state and unoccupied state. In fact, in more regular temperature, we are probably closer to the green as fairly high temperature. So it's always also a very sharp transition between the occupied and unoccupied state. So in particular, for metals, it's when you have basically the density of state, which is continuous across EF. That's basically the idea. It turns out that EF is a large number. And there is, again, it's another definition. We can introduce a Fermi temperature, just like we introduced the Einstein temperature, the Debye temperature, and so on and so forth, which is just a rescaling by remembering that kBT is an energy term. So basically, you can get a Fermi temperature by dividing EF by kB. And that temperature is very large for metals. And because of it's very large compared to typical temperature, this is another way to saying that we have a sharp transition here. Basically, think a little bit about EF as a scaling factor of the entire problem. So the scaling factor is EF, and that means that everything can be expressed in terms of that particular reference energy, and that's the reason why we have behavior, like I said, with a sharp transition between occupied and unoccupied states. So we have what we call the degenerate limit, in the sense that we have pretty much mostly occupied state, and then non-occupied state. This is the idea. Now, one thing that's important to know is, and I should insist on this, is that for example, consider electrons in a molecular system. The electrons that you will be able to excite are those that are low energy, so those that are closest here. They can be the most low energy compared to the chemical potential. So these are the particles that you will easily excite. So most of the physics, in fact, most of the chemistry in bonding happens with electrons that are around the chemical potential or the Fermi energy at t equals 0. So the reality is that you can describe very well most system with Fermi system at least at reasonable temperature by the behavior of the particles close to EF. And in fact, if you calculate the average energy of the system, just as with the usual equation, you find that the average energy, in fact, is directly proportional to EF. So which again makes sense that most of the properties will be described by EF. You can calculate the bulk modulus. Bulk modulus, we've introduced this before, is basically the change in pressure. So change in stress as a function of volume. And one more time, we have to normalize by 1 over v. So basically, we have to normalize by v, and we have a minus sign so that we have a positive number, since the volume usually decreases when you increase pressure. But you can calculate all this, and then you find the bulk modulus again will be proportional to EF. Again, showing that what really matters is what happens at EF for those cases. And you can also, in fact, in order to calculate this, we use the non-relativistic limit connection between the internal energy density, so U over V, and the pressure. Again, an equation that we've used so many times in this course. This table here is a table of some well-known metal like lithium, sodium, potassium, copper, silver, with different densities, and calculate the EF, which is fairly large, and also calculate the various properties like the bulk modulus, and you can compare the bulk modulus with this approximation, and you see that the trends follow pretty well, showing that this description is pretty accurate. Remember that here we have non-interacting particles, so and then we which is obviously an approximation. Now we have worked at t equals 0. It's a good idea to consider finite temperature, and this is a place where I've made the conscious decision not to provide the math to describe this equation. This is an important integral. It's called Sommerfeld integral. People call it also Sommerfeld expansion, which allows you to consider F, so the Fermi-Dirac distribution, and to look at it from the perspective of temperature. So as you remember, it depends on kBt, right, the beta, and to see a little bit how we could describe this integral as a series of integral, basically, that allow us, a series of terms that allow to look at temperature effect. And of course, each temperature at higher and higher power has less and less importance because the term in front is smaller and smaller. So this is the idea, and this is called Sommerfeld expansion. And if you're interested in the proof for this, I invite you to look into our favorite reference book, Blundell and Blundell, which is going to provide you the proof of this equation. So we have many times over this type of integral, and we are going to consider it. So let's consider the number of particles first, and we are going to limit ourselves to the spin 1/2 systems. It's not really a limitation. It's just to make our life easier. Instead of having to carry over 2s plus 1, we are just going to carry 1. So that's going to make things much easier. So we can calculate again the number of particles. This is the equation I already showed you a number of times. But this now we are going to focus on F at finite temperature. So instead of just looking at t equals 0, we're going to look at the finite temperature. And we are going to use a Sommerfeld expansion for this integral. And the Sommerfeld integral is going to provide this here. So this is a little bit opaque. These are equations that offer you a chance to look at how the number of particle changes with temperature. Opaque is that it's difficult to realize what the physical effect of this is, but these are equations that are very much used when you look at finite temperature effect. More importantly, you can also calculate the chemical potential. Why I say more importantly? Because you see that the chemical potential is a function of temperature, is going to depend on this term here. But interestingly enough, the first term at t equals 0 is mu0, which is the Fermi energy, right? The Fermi energy by definition is mu at t equals 0. Remember a couple of slides ago. And then we also see that the correction at finite temperature is here. And in fact, that correction is pretty small, it turns out. It's a pretty small correction. That means that the Fermi energy does not change much with temperature. It does change, though. It does change. But it doesn't change drastically with temperature. In fact, we can rewrite it this way. This is the same thing here, just written in slightly more compact way, not that more compact. And then we find that we can mu of t, mu of 0 is equal to EF. By definition, mu of t is almost equal to EF as well. And it's particularly true when EF is a large number. Very good. So remember, EF can be written as KBTF with the Fermi temperature, and all that matters is the ratio between KBT and KBTF. That's what's going to give you the measure of how far you are from the Fermi energy. So all this, let's try. I mean, it's easy here to be lost in the math and say, wow, there's so many equations and so on and so forth. But here, what matters is to realize that everything we've done in the past 10 minutes is describing what happens for those fermions that have been added the last. Well, of course, there's no time effect here. Let's not worry too much when I say the last. I said if you start to fill up your bookshelf from the bottom. So those that you have added the last correspond to the energy EF. And so these are very important energies, because these are the energies that can more easily be excited to an occupied state. And so all we've done here is to really look at what's happening for those levels. And this is how we understand a lot of things in quantum mechanics, in nanoscience, in chemistry, and in material in bonding in general. So we can calculate a couple more things. Let's try to look at the internal energy. Why we want to look at the internal energy as a function of temperature is because it will allow us to calculate the heat capacity. As you know, the heat capacity is related to the first derivative of the internal energy with respect to temperature. So if we have a description of the internal energy as a function of temperature, we'll be able to do that. And the integral, again, is an integral we've seen a number of times today, is provided here. You can apply Sommerfeld expansion to this equation. And one more time, remember, Sommerfeld expansion is about understanding the effect of temperature coming from this term here, which is a Fermi-Dirac distribution, which depends on beta, right? So we end up with this particular equation for the internal energy. We, of course, recognize, again, what we discussed before. And then, yeah, so we can calculate the heat capacity as the derivative of this with respect to temperature. And what we find, interestingly enough, is that the heat capacity at constant volume is actually changes linearly with temperature. So what's good is that when t equals 0, this is equal to 0, as we would expect. But remember, again, the lecture that we've done on the third law of thermodynamics. But one thing that's interesting is that the heat capacity is actually a linear term with temperature. Now, some of you might be confused, because you might remember that the heat capacity that we have described when we did Dulong and Petit equation was actually as a cube, going as a cube at temperature. But those equations in the Dulong-Petit were for phonons. So what we found there is that for phonons, the heat capacity goes as T cube. And in fact, at a reasonable temperature, most of the heat capacity is due to phonons. So this is basically when you add energy to a system, it's going to be stored into the vibrations of the lattice. But it turns out that you can also add energy to the electronic, for example, in this case, electrons for fermions, as an example, in the electronic degree of freedom. However, in this case, the temperature dependence is linear. So at high temperature, it's basically going to be negligible, this particular thing, because of course it grows much, much slower than a cube. This is T cube is the Dulong Petit. And in fact, this is a picture here of the Dulong Petit. And you see that if you, this is actually a cube. You can see that by, remember, be careful, this is a logarithmic scale. There's a reason why it looks like a straight line. So when you have a semiconductor, you cannot excite electrons very easily. Therefore, the most of the contribution is from the phonons. So when you have a metal like copper, you see that the behavior that you expect, the Debye with the behavior, so the Dulong Petit, works pretty well. I mean, the Debye behavior that described that at high temperature fits the Dulong Petit. That's what I should say, probably more carefully. But the phonon part is pretty good compared to experiment. But at low temperature, this term here is actually a term that's related to the electrons. So you need to include the electrons are those that you are going to excite at very low temperature first. So the heat capacity will be the electrons. So that's quite interesting, because that also shows us that as you go lower and lower in temperature, you have other aspect and other effect that you can start to see as well. The last thing I want to say is that I would like you to remember that we are working with those wave vector, where the space where the wave vector lives. I discussed that when we have a system without any interaction whatsoever, we had this Fermi sphere, Fermi surface. So the Fermi sphere is basically, we know that there is a sphere in K-space that has all the same energy. And the reason why it's like this is because we have the dispersion relation, which is E equal to h bar square K square over 2m. So that's good. The Fermi surface now, if you, in general, is not necessarily a perfect sphere, because there are, of course, there's interaction between the particles. So what we call the Fermi surface is going to be that surface in the wave vector space, so in the K space, which has this correspond to the equal chemical potential. So basically, it's a surface that separates the occupied state from the unoccupied state in K space. So this you probably have seen Fermi surfaces before, or you will see some in the solid state physics course, for instance. And this is an example here for copper. So it's pretty close to the free electron model for copper is pretty accurate. It's almost a sphere. It's not quite. And you may wonder what is the shape here that you see with the square and so on, the hexagon and so forth. This is actually the shape that we used for in a reciprocal space. This is actually a Brillouin zone, but this is a little bit beyond what we are doing in this course. Now it's time to move to the Bose case, the bosons. So far we have spoken mostly about, at the beginning of this lecture, actually, we spoke about state systems in general. Then we looked at fermions. And the most important thing about fermions is that there is a maximum energy at which we put the state at K equals 0. And this is called the Fermi energy. And then after that, we can look at temperature effect. Temperature effect being to excite those electrons close to EF, because these are the electrons that can actually move from occupied to unoccupied. Now for bosons, it's completely different. Well, what's interesting about bosons is that, of course, the number of particles and the internal energy can also, we can use the same equation as we did at the beginning of this screencast. So I'd like to stress that at the beginning of the screencast, we look at both boson and fermion. In fact, we had plus and minus Z, or in fact, minus and plus Z. So they work both. And then we looked at the specific case of fermion, and now we are going to look at the specific case of boson. So we have those two equations that we've seen before, and we can, if we look at them for mu equals 0, and the reason why we look at mu equals 0 is because it's going to be an important thing to look at in a minute. But imagine for now that we look at a chemical potential equals 0, and again, I'll justify all this in a few seconds. If mu equals 0, the fugacity is equal to 1, and therefore I can replace this equation by I can replace the polar logarithm function by the zeta, the Riemann zeta function, and then this is what we do, and then we obtain this function. So what's interesting is that these zeta are actually numerical you can actually look at tables and find the numbers for what they are. So you can actually replace. I'm sorry. You can actually replace these numbers, these value by numbers. So this is just to show you how to do this depending on the value of mu. So here we just look at mu equals 0. I'd like to remind you though that all those equations were we had to use the density of state. We had to integrate, and this is how we introduced the Poincare logarithm function. And the density of state predicated on the fact that the energy is given by this term. This is not always true, though. And in fact, there is a very important class of boson which does not follow this relationship. These are called photons. A photon, as we've discussed in the lecture on the ultrarelativistic gas, do not have this dispersion relation. In fact, the dispersion relation for photon is a linear relation with h bar kc. So everything we've done so far cannot be used for photons. I'd just like to be clear, since we have used a different dispersion relation for the energy. But let's have a look on this slide what would happen if we use a photon case. So for that, the only difference you have to do compared with what we've done before is to look at the density of state. This formula is still the same as before, but the second line is not the same as we've done before because the dk, so k squared dk, is actually now, turns out that k squared dk can be related directly to dE and D and E, because there is a linear relationship between A and K, and with just h bar c as of course come as a cube, as we imagine, because we have a cubic term k squared dk. Anyway, the point is that this is the density of state we want to use if my dispersion relation is given by this. I'd like to say one thing here, and I'm not going to dwell too much on this, but I have to mention it. It turns out that this number here for photons is actually only 2. We don't have 3. The reason why it's only 2 is because we only have 2 polarization possible. As you may know, a photon cannot have the polarization 0, and cannot have the projection 0. And because the projection 0, and I have a small text here that I'm not going to read, but the point is that justifies why we only have 2 polarizations. But the point is, if we had a projection 0, that means that the momentum would be pointing perpendicular to the direction of propagation. And this is not something that's possible for a photon which actually does not have a rest frame. So that's the idea. A photon will travel at speed of light no matter what the frame the reference frame you use. And if you had, in order to have a momentum perpendicular to the direction of propagation, you would need to be able to find a rest frame which does not exist. So that means that you have only 2 polarizations possible. This is not the object of this course. I just want to open this parenthesis. So we can repeat everything we've done before with this new density of state. And again, this density of state work for this dispersion relation. And then we get another integral. And then, of course, we get integral like this. And we can calculate. It turns out those integral also follow this integral that we've introduced before with the Poincare logarithm function. And what's interesting is that after everything is said and done, we find that the internal energy is here. Why do I this while smiling? Because it's exactly the result we found when we did the Stefan Boltzmann constant. This is exactly the result we find in chapter 23, which is not a big surprise since we are using the same approximation and same idea. Remember, chapter 23, we were looking at the black body radiation, and this is the internal energy we have for photons at temperature. So we see that the internal energy goes T to the power 4, and the terms in front is the Stefan Boltzmann constant. So this is the result we would have for this particular linear relationship. Now let's have a look at let's go back to the description with E equal h bar square k square over 2m, and then we'll see that this description is going to lead to a conundrum that we are going to try to solve and this screencast. So the energy, as we said, if we want to work the energy like this, which would be the case for, like say, a free particle, what we see is that k equals 0 will lead to the energy has to be equal to 0. Fine. So the lowest energy for in this particular model is E equals to 0. Now, remember that we discussed that the chemical potential for Bose-Einstein distribution has to be at most equal to the should be actually lower than the ground state. The reason for that is there is basically a divergence at when E is equal to the chemical potential. And again, I invite you to go back to the previous lecture, or maybe to just look at the Bose-Einstein distribution, and you will see that you would get 1 over 0, so you get an infinity when mu equal to E. Well, but the point is, because E equals 0 is a possible state, you can't have mu equal to 0. So mu has to be strictly negative. This is just a fact. Otherwise, you would have either an infinite occupation of a state or a negative occupation of a state, which is not possible, right? So if you remember what the fugacity is, and I promised you I would reintroduce the definition a couple of times so you would remember, the fugacity is here. Beta is a positive number, is 1 over kBt. Mu has to be negative, right? It has to be negative simply because it has to be lower than the lowest energy available, and the lowest energy available is E equals 0 at k equals 0. So that means that beta is positive, mu is negative. So Z is of course a positive number, but it has to be strictly smaller than 1. And the strictly here is simply from the fact that we have mu is strictly lower than 0. Okay, very good. Let's try to, and it's also strict here because, well, we'd never reach the value that would yield exactly 0. So let's have a look now. So we have for the boson Z that we use for both fermion and boson has to be at between 0 and 1. Now let's go back to the equations that we introduced a couple of slides ago for the number of particles. We find that we can rewrite this, okay, because we can just rewrite this so that on the left hand side we have n over v, which is the density, and then we can just promote everything on the right hand side to the left hand side, and we find this equation. Okay, fine. We also know that the thermal energy, the thermal wavelength, sorry, depends on the temperature. Okay, so good. So that's going to become important. Now here's the thing. This is the behavior of this polylogarithm function between 0 and 1. Remember, Z has to be comprised between 0 and 1. So this is what we get. Okay. So the problem is between 0 and 1, this number here is bounded between 0 and the value of the Riemann zeta at 5/2. I'm sorry, this is the one I have to look at, between 0 and the zeta function at 3/2. The point is, it's this number here is between 0 and 2.5, something like that, this point here. It's actually more like 2.6, turns out. Okay, let's try to see here. Let's suppose that experimentally you have a gas of boson, and you decide to increase the density, or if you can't increase the density, you want to decrease the temperature. So decreasing the temperature will increase the thermal wavelength by the definition of the thermal wavelength. Okay, so basically we are increasing this number, and we can increase the density or we can decrease the temperature. I mean, these are things that can be done experimentally, I would say. I'm going to show you examples of that in a few minutes. So basically, this term on the left can be modified, and this term on the right, of course, is a number. Okay, it's going to be a number when I get close to z equal 1. So if mu increases, so if we get a mu that's larger and larger, but still strictly smaller than 0, we get close to this point here, z equal 1. Not quite at z equal 1, but close to z equal 1. And so that means that we are approaching mu to 0 from below, right? Mu being negative. Mu being negative, correct? So in other words, as I said before, this term here, if this term here is larger than this number, right, at z equal 1, we will not be, there is no solution, right? So if this number is larger than this value, because it's a monotonic function, if this number is larger than this value, there is no z that corresponds to it. So let me try to repeat. We have this here, this term. If we experimentally prepare a system with the right density and temperature, right, and then we find a chemical, and we use a chemical potential that's very close to zero, but still negative, it has to be, there might be a way to create a system for which the left-hand side of this equation will be larger than 2.6. But if it's larger than 2.6, there is no fugacity that corresponds to it. There is no value of z that corresponds to it. So there is a problem. There are two solutions to this problem. The first one is that physically you can't do this. You just simply cannot reduce. You can't increase n and reduce temperature so that you get this. Or the other solution is that we made a mistake somewhere. Well, it turns out we made a mistake somewhere. While the mistake is a little bit subtle, it turns out it's one of those mistakes that we make when we forgot about the assumptions we made. And the big assumption we made is to replace the sum over the k state by an integral over the k state. So this approximation works very well. For fermions, it certainly works very well. For bosons, it works very well most of the time, but does not work very well all the time. The reason being that when you start to be at very low, when you start to be at very low temperature, and then your chemical potential is almost zero as well, you are only occupying one state, right? Think about that. If t equals 0, there is no thermal energy to excite system above the ground state. So basically, you have a distribution of state that has a peak at the ground state, right? But clearly, you cannot replace the sum of a single state by an integral. Does that make sense? Yes, because it makes sense in the sense that we have the discrete nature of the state cannot be replaced at t equals 0. T very small t cannot be replaced by an integral. And let's try to understand this a little bit better. And in fact, what I'm going to explain to you now is going to show that at very low temperature, there is a different phase of matter, to speak, which is called a condensate. And condensate, the Bose-Einstein condensate, is actually that state where most of the bosons are actually in the ground state, and they all live there, and that's going to resolve this problem. So I'd like to say here, before we move on, here, compared to the previous slide, this is basically the temperature. We call it critical temperature. This is the temperature at which the inequality from the previous slide was reached. And what I've done compared to the previous slide is to reintroduce the definition of the thermal wavelength into the problem. That's how now we can see more explicitly the temperature from the thermal wavelength. So the point remains is that if the temperature reaches this and below, we don't have a solution of the inequality I had on the previous slide, and therefore we have to treat our system using the sum, I would say, instead of the integral. So that state becomes macroscopically occupied. That means that most of the particles go into a single state. So we have a condensation. All the mathematics break down, and then that happens below this temperature. So let's try to see a little bit if we can understand this just a little bit more. So the best way to do this is we are going to consider, and we're going to set the energy of the ground state as 0. It makes sense. And then we are going to suppose that the total number of particles will be the number of particles in that state 0 plus the rest. So the idea being that we are going to treat the state the ground state as an individual state without having to worry about density of state and integral. And we are going to treat the rest using the approach that we have used so far, so the density of state. So we are going to mix those results, and that should work well. We'll see. So the total number of particles, as I said, is the particle in ground state plus the rest. This is what's here. N1 is not the first excited state, okay? N1 is the rest, all the others that are not in the ground state. Okay, now if we are above TC, we are, okay, Z is smaller than 1, and we have N0 boson in the ground state. So we are above the critical temperature, and we have N0 boson in the ground state, which is actually a pretty small number. In fact, if you look at if you calculate its, if you use the Bose-Einstein distribution, you find an N0 is simply obtained by this equation that we've seen so many times. The reason why this equation is correct is because we put the ground state energy to 0, right? Otherwise, there would be a plus U term in here, a plus E term in here. Okay, so we have this particle distribution, and then we can of course write it as a function of the fugacity, since the fugacity is e to the power beta mu. We can write this number of particles here as a function of z. So if z is smaller than 1, so not 1, this number, this N0 is actually pretty small, right? It actually gets pretty small unless it gets to 1. But let's suppose we are not at 1 for now. And we are not at 1. This is since we are above TC. Okay, it's all related, of course. So most of the particles, it turns out, for above TC, or well above TC, should I say, most of the particle will be in N, will be in the excited state. Indeed, there are so few particles in N0, all the rest have to be in N1. So basically, most of the particles are in N1, and we can use the formulation that we've used so far for the gas, where we use the density of state. So that's fine. We can do that. It's just that we have now separated the state, the ground state, and from the rest, which is fine. Okay, good. Now at TC, the things start to break down a little bit. When we are at the critical temperature, the density of boson, which is the total number of particles divided by the volume, are going to be obtained, for example, from this equation that we have also described before. This is going to be my total number of particles, and then we can calculate N1 as well. So we can calculate N1, and if we calculate N1, the N1 will be what we had before at the regular temperature. Okay. So below TC, so the density of state, so once we get to that place, Z is extremely close to unity, and we can make the approximation Z equal 1 at below the critical temperature, and then we can calculate the number of particles that are not in the ground state 0. So that's going to be obtained by this equation. And of course, here the approximation we make is that Z equal to 1. But the density of particle in the excited state is going to be obtained by this equation that we've seen before. There's nothing new other than the fact that we are just looking at the state. We are just looking at all the states that are not N0. So the rest of the particle, so now we know how the total number of particles, the density of particles, this is the particles that are in the excited state. So of course, the rest, the ones that are not in N1 must be in N0 by definition, right? So we calculated the total density of particles, all of them. We calculated the particle in the excited state, and the difference is going to be in N0. Okay, nice. So all this, you consider that we are looking at continuity. So we have this total number of particles, we have the total number of particles that are not in N0, and of course what's in N0 is the difference. Okay, so first of all, and this is something that's very important, is that we can calculate the ratio between these two so that we get rid of all those constants, and in fact also the constant in thermal wavelengths, and then we find that the ratio between N1 and N, so the density of particles in the excited state versus density of particles, the total particles, we obtain this as a ratio between T and Tc. And of course, now that allows us to calculate N0, the density of particle that are in the ground state. So the ratio between N0 and N is simply the difference between the total number of particles minus those that are in excited state. And we obtain this equation. That's a very simple equation, in fact. So the best way for this is to plot it. And this is how N0 over N is a function of T over Tc. So here's the thing. When you are when you're at very large temperature, you see that actually this is only valid in this area, in this region. But what you see is that between 0 and 1, when you are at very low temperature, let's say at 0 temperature, 0 Kelvin, you don't have enough thermal energy to excite any boson. So there must be in the ground state, right? So that's the reason why the total density is 1. But as you see that below Tc, which is only the area where this thing is valid, of course, because after that we have negative numbers. Below Tc, okay, we see that many particles, most of the particles, will be in fact in the ground state. And the fact that they are all in one single state, and let's try to remember here, when we talk about the density, we are talking about huge amount of particles. We are talking about million, trillion, Avogadro number of particles that are all in one state. So that's what we call a condensate. So we call that the Bose-Einstein condensate. So the Bose-Einstein condensate comes directly from the fact that we have to do the right statistical analysis used to the fact that the quantum state has to be symmetry under exchange of particles. So this is a very important result. Of course, I'm providing you here a fairly bird eye view of the problem, but it's just to provide you the conceptual reasons why we have this. One thing that's important to notice that very often is not well understood, or well, at least not remembered, is that all the states that we have looked at are labeled in K space, right? We use the K as the label, the quantum number, and of course that means the condensate is also in K space. So the condensation is not like you would say condensation of water on a windshield. Is actually a condensation in K space. So you see the two things that we've seen. For the Fermi, because of the very different quantum statistics, we describe a gas of fermion by Fermi surface, and for a Bose-Einstein system, a boson that follows Bose-Einstein statistics, we see that the description is at very low temperature. We have a condensate. So these are very two different limiting cases for physics, even though the equation looked very much the same. It was just a sign difference. So you can actually go further and study the fugacity, how the fugacity changes as a function of temperature, and so that you understand things a little bit better. The fugacity is never quite equal to 1. It's almost equal to 1, and you see that there is this change when above the critical temperature. We can also look at the internal energy of this problem as a function of the temperature at the left and the right of on the left and on the right of the transition. So one thing I like to say is that you have to be careful here when we talk about phase transition. We have a transition to a Bose-Einstein condensate, but this transition is not the same type that we've looked at before. When we spoke about phase transition before, it was due to interaction between the particles, right? Remember that it was the van der Waals model that allowed us to look at interaction. Therefore, there was a phase where we have a liquid coming from a gas, for example. Here, we still have non-interacting particles. I'd like to, again, insist on this. We have non-interacting particles only in these models that we have here. So this phase transition is really a phase transition due to the manifestation of the Bose-Einstein statistics at low temperature. So there are a number of examples where we can actually apply this equation. One famous example is the dilute gas of alkali metals. And so this is a fascinating subject. The idea here was to look at a very dilute gas of alkali metal. So it's not many atoms actually. It's between 10,000 and a million. They were trapped and cooled using laser cooling. The idea here is um, to couple them with a magnetic field, and this is how it works. So you can. It turns out that the spin of that system is actually an integer. So we have bosons, and you can in fact get all those states, all those particles in the same at the same state at below a certain temperature. Turns out that because the mass of the system and the mass is pretty large and the density is low, if you look at this equation that we have described before to describe the critical temperature is tiny, is extremely small. However, one of the big things about the laser cooling is that you can go very, very, very low temperature for those systems. And even though the critical temperature is 10 to minus 8 Kelvin, which is of course very small, it was doable to do it. It was possible to reach those temperature using the laser cooling. And of this system of boson. And in fact, that led to the observation. This is of this condensation of a metallic atom, alkaline atom. This is an image specific to rubidium atoms. This is before the critical temperature, and it's at critical temperature and it's below critical temperature. So in fact, that was a big deal. It was one of those new physics that's being described, and this was the subject of the 2001 Nobel Prize. It was awarded to two groups: one who looked at rubidium atom, and one group who looked at sodium atoms. So all those could be done with cooling of the atoms, and basically see this new phase of matter. Uh, there is another example I meant to mention, and you know, of course, electrons are fermions, therefore they do not follow Bose-Einstein distribution. However, you can combine fermions to have bosons, and one example of that is superconductivity, or at least the BCS superconductivity. As you might know, there are a number of ways to describe superconductivity, including ways that we don't know yet, I should say. But in the early days of superconductivity, there was the so-called BCS theory of superconductivity. And in that case, everything could be explained by the fact that you create a Cooper pair. A Cooper pair is a pair of electrons, so fermions, that actually are bosons. And the reason why they would couple, even though they should be repulsive due to the electrostatic potential, is because this interaction is mediated by phonons, vibrations of the lattice. So this is a fascinating subject that goes a little bit beyond the scope of this course. But the point remains that you can create those gas, basically of bosons, and a boson here is a pair of electrons, a Cooper pair, and you can actually explain what's happening as those condensate, basically. So this is the BCS theory. It was BCS actually means Bardeen, Cooper, and Schrieffer, who came up with the description of this. So for those who are curious to know how a lattice vibration can lead to coupling between electrons, imagine that as an electron goes through the lattice here, let's imagine the electron is negative. Let's suppose the ion are positive. Because the electron goes through the lattice, the ions are going to be slightly attracted to the electron, right? They're going to be slightly attracted to the electron. So there will be a slight, of course, this effect here is exaggerated. But now imagine there is another electron close by. Well, the other electron close by is going to see this as an attractive center due to the ions. Therefore, it's going to be attracted by this. So it will look like the second electron is attracted to the first electron. So this effective attraction is due to is actually mediated by the lattice vibration, and then therefore what results from this is two electrons that look like they are attracted to each other, but this is mediated by the lattice. So that's a fascinating subject. Most of the superconductivity that's being studied right now, which is high temperature superconductivity, does not follow this model, but there is room there for further work. So this is going this conclude this screencast, which was pretty heavy in mathematics and also heavy in concept. So I hope that you enjoyed this and you learned something. The summary is that we look at both fermion and boson. One important concept for fermions was the Fermi energy, which was basically due to the fact that we have to fill up, we can only fill up an electronic state up to a certain level. We also saw that the Fermi, this level is important, this Fermi energy, because this is where most of the interesting physics and chemistry happens, is close to the Fermi energy. Why? Because these are the particles that can most easily be excited. They are the one that require the least energy to be excited. Okay, we also look at the Bose-Einstein case. We spent quite a bit of time, and in fact, we spoke about condensation, where we have the condensation is basically a breakdown of this continuous modeling of the Bose-Einstein description, and we have to consider a single state, which is the ground state, for which we have a macroscopic occupation. And so this macroscopic occupation in reciprocal space, so in wave vector space, is so large that we can call it a condensation, and which is another phase of matter. Thank you very much.